Uh, Hello all. Today I want to cover for you section 6.2. In 6.2, we are discussing exponential functions and their derivatives. Not only derivatives, I will cover for you some limits of exponential functions and also integral of exponential functions. Let's start with the basic of uh, or with the definition of exponential function. Which kind of functions? We call them exponential functions. An exponential function is in the form of f of x equals b to the power of x. Or sometimes even maybe you see in the past y equal b to the power of x. Because we are talking about function, then we use usually the function notation, which is we can write f of x equals b to the power of x, correct? Here, b is a positive constant, correct? Your b is a positive constant. For example, f of x equals 2 to the power of x. I will call this function an exponential function, or f of x equals 1/2 to the power of x. The difference of this function with the other function is that your variable is in the exponent. That's why we call it exponential function, 2 to the power of x, or 1/2 to the power of x. But anyway, your b is a positive constant. 2 is a positive number. 3 is a positive number. 4 is a positive number. Any positive number to the power of x, or numbers between 0 and 1. 1/2 of to the power of x. 1/2 is a constant. It's a positive constant, right? Now, when we write b to the power of n, what does it mean? It means b times b times b. It means you have n factor, of b. Correct? Because I see this mistake a lot. Sometimes when I'm writing 2 to the power of 3, immediately I get an answer. Okay, how much is 2 to the power of 3? Immediately, some of the students, they say, oh, 6. 2 times 3 is 6. No. 2 to the power of 3 means 2 times 2 times 2. N factor of 2, 3 factor of 2, which gives you 8, right? You can't afford such a small mistake in calculus class, especially in calculus 2. If you have 2 to the power of 3, immediately you write 6, you can't afford such a mistake. You have to be careful. You have to know the meaning that 2 to the power of 3 means 2 times 2 times 2 times 2, which gives you 8. Now, few notations or few exponents that you saw before. If you have b to the power of x, right? When x is equal 0, if x is 0, you will end up definitely with b to the power of 0, and any number to the power of 0, the value is 1. Correct? Now, if you have again b to the power of x, and your x's equal negative n, definitely you end up with b to the power of negative n, and from algebra you know that we can change a negative exponent by sending it to denominator, correct? Which is equal 1 over b to the power of n. One more, if you have b to the power of x and your x is a fraction, for example, a fraction of p over q, right? then you end up with the b to the power of p over q. We call this notation exponential notation, but you can change it to radical notation. B to the power of P over Q means the Q root of B to the power of P. You can do this, or you can do the Q root of B all to the power of P. You can change it to radical notation. Or if you have a radical notation, you can change it to exponential notation. Correct? Few more notes. If B is greater than 0 and your B is not equal to 1, then you can say f of x equal b to the power of x is a continuous function with the domain from negative infinity to positive infinity, or you can say this way, all real number. In your book, they use this R. It means all real numbers. The domain of your function is all real numbers, and range of zero to infinity. Because b is always a positive constant, b cannot be negative. B should be always greater than 0. Also, b cannot be equal to 1. Why not 1? Because 1 to any power gives you 1, you will end up with a straight line. Soon I'll show you in the graph. B cannot be 1 and b should be always equal to 0. Then you end up with such a graph, which is the graph of b to the power of x. Maybe the graph goes this way. This is y, this is x. And this graph represents f of x equal b to the power of x, right? You see, your domain is from negative infinity to positive infinity. But range always starts from 0 to positive infinity, correct? And it's a continuous function. There is no hole, no break, no gap in this function. That's why we call it, it's a continuous function. Now, few more notes. If you remember from algebra, again, I'll repeat here, you will end up with two types of the graph of b to the power of x. Number 1 or note 1. If your b is less than 1, greater than 0, it means all the fractions between 0 and 1. In this case, f of x equal b to the power of x is a decreasing function. It means you will end up with a graph like this. This graph represents f of x equals b to the power of x, but your b is less than 1, greater than 0. Let's do a numeric example. For example, If you graph f of x equal 1/2 to the power of x. Your b is 1/2, and 1/2 is between 0 and 1, right? Let's graph this and see what's the shape. If this definition is true. X, y, let's plug in few numbers. For example, let's start with 2, 1, 0, -1, and -2. When x is 2, you end up with 1/4. When x is 1, 1/2. When x is 0, 1. When x is -1, I'll show you the -1. F of -1 equals 1/2 to the power of -1. And you learned in algebra, when your exponent is negative outside, you can flip the inside and change this exponent to positive, which gives you 2/1 to the power of 1, which means 2. Same way, f of -2 equals 1/2 to the power of -2, which you can flip the inside, 2/1 to the power of +2, which gives you 4. Let's plot these points and see the graph if the definition is true, right? I'm trying to show for you on a numeric example that when b is less than 1, greater than 0, your graph is actually decreasing. Let's plug in these numbers. When x is 2, y is 1/4. x1, x2, y is 1/4. Something like very close. If I divide 1 unit to 4 equal pieces, something like a point here. When x is 1, y is 1/2. 1.5 will be here. When x is 0, y is 1. When x is -1, y is 2. And when x is -2, y is 4. You see, if I connect these points with each other, this one will be the graph of f of x equals 1/2 to the power of x. You see, 1/2 is less than 1, greater than 0, which is your b. When b is greater than 0, less than 1, your function is actually decreasing. You see, the function is decreasing. Or if you remember from algebra, we call these functions, which they are exponential functions, that they are decreasing, exponential decay, correct? That's like the graph of exponential decay. Note number 2. If b is greater than 1, in this case, f of x equal b to the power of x is a increasing function. Again, to show it in a graph for you, here is one. When your b is greater than 1, this function will be increasing, right? You end up with a function that passes from 0, 1, and it's an increasing function. And if you remember from algebra, we call these exponential functions exponential growth because it's increasing, right? One of the main characteristics of these exponential functions is that all of them, they're passing from the point 0, 1, all of them. any function. If you see 3 to the power of x, 12 to the power of x, 1/2 to the power of x, right? For example, let's say 3/4 to the power of x. Any of them that you graph, all of them is passing from 0, 1. It's the main characteristic of the exponential functions. Some more notes for you, then I'll slowly go to the examples. We will start the calculus of exponential functions, right? Some laws of exponential functions that's important for us to, once again, to review. If your b is greater than 0, it means b is a positive constant, and you have x and y as exponents, but they are all real numbers. They are in R, right? Then we can write these rules for you, which is again a review. I'm sure most of you remember these exponential rules. If I have b to the power of x times b to the power of y, I can write this one as a b to the power of x plus y. Or opposite, if I have b to the power of x plus y, I can separate as a b to the power of x times b to the power of y. You know, it's an identity, it's a law that can apply both ways. To show a very basic numeric example for you, I can say if you have 2 to the power of x times 2 to the power of y, you can write this one as a 2 to the power of x plus 1. Correct? Rule number 2, or law number 2, if you have b to the power of x over b to the power of y, in this case, you can write b to the power of x minus y. Right? Numeric example, 2 to the power of x over 2 to the power of y equals 2 to the power of x minus 1. Rule number 3, which we call it the power rule. If I have b to the power of x all to the power of y, in this case, we multiply the exponents. It will be b to the power of xy. For example, 2 to the power of x all to the power of y equals 2 to the power of xy. Last, number 4. If I have a times b to the power of x, in this case, you are distributing the exponent to both bases, right? It means a to the power of x times b to the power of x. These 4, we call them laws of exponents, right? Plus the other 3 that I put at the beginning of the lecture for you, that b to the power of 0 is equal 1, b to the power of negative n equals 1 over n, b to the power of positive n. We call all of them the laws of exponents. Now, let's start slowly the calculus of exponential functions. First thing that I want to cover for you is limit of b to the power of x, or limit of exponential functions. Number 1, if b is greater than 1, then the limit of b to the power of x as x approaching to infinity gives you always infinity. What does it mean? Let's explain this part. when b is greater than 1. For example, if you have a function f of x equals 2 to the power of x. 2 is greater than 1, right? And I explained to you, when b is greater than 1, your function is actually increasing. It passes from 0, 1, and it's an increasing function. It's like this. Now, this rule, the limit of b to the power of x as x approaching to infinity. You see, when your x is moving this way, when you are approaching to positive infinity, where the function goes. When x goes to infinity, your function, which is b to the power of x, is increasing, 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 increasing. It goes also to positive infinity. That's why increasing, 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 or we say as x is going closer, 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 closer to infinity. Hopefully your professor in Calculus 1 explained this way to you, that when we say closer, 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 instead of repeating closer, 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 we use the word approaching. As x is approaching to infinity, your function is also approaching to infinity, and we write this as a notation of limit. The limit of b to the power of x as x approaching to infinity gives you infinity. And also, the limit of b to the power of x as x approaching to negative infinity, it gives you always 0. Look at the graph. Look at our graph. When your x is approaching to negative infinity, this is the function b of x, right? P of x is coming closer, 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 closer to x-axis, but it never touches the x-axis because the x-axis is the horizontal asymptote for the exponential functions, correct? It doesn't touch the x-axis, correct? It means it's coming close and close and close to where? To 0. Then you can write the limit of b of x as x approaching to negative infinity is always 0, correct? Number 2. If b is greater than 0, less than 1, then the limit of b to the power of x, please, this is my notation for limit. Let me explain to you, I cannot write limit, I don't know why, like this. Everyone likes to see my limit in this way, but I do this as a limit. When I write something like this, take it as a limit, right? I cannot write LIM for some reason, I don't know why, correct? This is my limit. Limit of b to the power of x as x approaching to infinity always gives you 0. Let's see it on the graph. We just explained when b is between 0 and 1, you end up with exponential decay, or your function is decreasing, right? Like this. Here is 1, here is 0. Now, as x approaching to infinity, where the function goes, where b to the power of x goes, it's coming close, 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 close to where? To 0. That's why you can write all the time, when b is less than 1, greater than 0, then the limit as x approaching to infinity gives you always 0. Number 2, the limit of b to the power of x as x approaching to negative infinity, it gives you infinity. You see, when your x is approaching to negative infinity, your graph goes to infinity. Right? 2 more rules. These are really important. When you deal with the limit problems of exponential function, you have to remember these rules, correct? Which I put 4 of them for you. 1, 2, 3, 4. Correct? If I make a table to memorize, you need all these 4. Number 1, limit of b to the power of x as x approaching to infinity when your b is greater than 1, it always gives you infinity. Number 2, limit of b to the power of x as x approaching to negative infinity. When b is greater than 1, it gives you always 0. Number 3, limit of b to the power of x as x approaching to infinity. When b is less than 1 greater than 0, it always gives you 0. And the limit of b to the power of x as x approaching to negative infinity, when your b is less than 1 greater than 0, it always gives you infinity. These 4 you have to memorize, you have to remember them, because when you are dealing with limit of exponential functions, you are using actually these 4 ideas to do the limit. Now I'll show you an example. Right? Example number 1. Find the limit of 2 to the power of negative x minus 1 as x approaching to infinity. 2 to the power of negative x, I can write this one as a positive exponent. Then I can write the limit of, instead of 2 to the power of x, I can write 1 over 2 to the power of x minus 1 as x approaching to infinity. Correct? Now, based on the rules of the limit, you can write the limit of, instead of 1 over 2 to the power of x, can I write 1 over 2 all to the power of x? The only reason that I can write this is because I have 1 in the top, right? And 1 to any power gives me back 1. Then instead of 1 over 2 to the power of x, I can write 1/2 to the power of x minus 1. I'm changing my notation. Why I'm changing notation? Because I want to use one of these 4 rules of the limit, right? Now, separate the limits. You can write the limit of 1/2 to the power of x as x approaching to infinity minus limit of 1 as x approaching to infinity. Limit of 1/2 to the power of x. You see, 1/2 is less than 1 greater than 0, and x is approaching to infinity. If I check my rules, the 4 rules, when b is less than 1 and greater than 0 and x approaching to infinity, your limit becomes 0, right? Now I can write here as a, this part becomes 0 minus the limit of a constant. When x is approaching to infinity, always gives you back the constant, cut 1, right? Which you end up with negative 1. They are really easy. This part that I changed 2 to the power of negative x to the 2 to the power of x, it's all algebra. Why I changed? Because I want to change my exponential part to the form of one of these 4 laws of the limit that I have in my table, right? That was the reason that I changed the form. One of the main exponential functions that they have a lot of use in the real life, and especially when you're studying calculus, it comes occasionally in different parts of the calculus, is function e, or e to the power of x. Everyone knows the value of e, it's 2 point something, right? This function, which we call it exponential function e to the power of x, it comes a lot when you're dealing with calculus. What is e to the power of x? To explain to you, for you, e to the power of x is also an exponential function which passes from 0, 1, and the shape is like this. This is e to the power of x. This function e to the power of x is a function that's between the 2 to the power of x and this function is between 3 to the power of x. That's why the value of e is 2 point something, because it's between the 2 to the power of x and 3 to the power of x, correct? Then any function f of x equals e to the power of x, we call it exponential function base e, right? And the graph is like this. Now, the main characteristic or the important characteristic of e to the power of x is that this is the function of graph of e to the power of x. If you look for the slope of the tangent line at this point, 0, 1, the slope of the tangent line at this point, your slope is always equal 1. That's the important part. That's the only exponential function that at 0, 1, the point 0, 1, the slope is always 1. Correct? If this is the case, then I can write a very easy, if I talk about the derivative of this, derivative of e to the power of x, I will easily say to you, this is the easiest derivative, that d over dx, or the derivative of e to the power of x, always gives you back e to the power of x. This is the simple derivative that you ever see. Derivative of e to the power of x is e to the power of x, always. But sometimes they gives you like this, e to the power of, for example, x squared, or e to the power of sine x, or e to the power of, let's say, 3x, negative 3x. You see in these examples, here x squared, sine x, negative 3x, they are a function, right? They are, we can name them g of x, e to the power of a function. When you have e to the power of function from calculus 1, you know that you have to apply the chain rule to find the derivative of this function, right? Then I'll put a different notation for you when x is a function or x is a g of x. In your book, it says when you have d over dx of e to the u, let me explain for you, u is actually a function, g of x. When you have e to the power of a function, in this case, your derivative, you have to go this way. E to the u times du dx. It means the derivative of this function based on u times the derivative of the exponent, du dx. Correct? That's the main formula that you use all the time, because sometimes it just gives you e to the x. Okay, if it's e to the x, the derivative of e to the x is e to the x. But if I have e to the sine x, then how to find the derivative of e to the sine x? We are using this formula. Let me show it for you. For example, if I ask you, find the derivative of e to the power of sine x, correct? Then d over dx of e to the sine x equals, sine x is actually u, right? Your u is sine x. It's a function, or I can name it even g of x, correct? But usually we use u for substitution. That's why we use u as sine x, correct? Now, the derivative of e to the power of sine x will be e to the sine x, or e to the u. Based on my formula, e to the u, and my u is sine x, right? It means e to the sine x times du over dx of, times du over dx. What is du over dx of sine x? The derivative of u in terms of x. The derivative of sine x is cosine x, right? It means d over dx of e to the sine x equals e to the sine x times cosine x. Correct? That's the explanation when you have e to the u, when e is to the power of a function. Do the derivative of e to the x, e to the u, times the derivative of the function. Chain rule. Correct? Let me do another example. For example, they're asking you differentiate. You have y equals e to the power of tan x. My formula is, if I have d over dx of e to the u equals e to the u times du over dx. That's my formula. Your u is here tan x, correct? Then du over dx equals, what is the derivative of tan x? The derivative of tan x is secant square x, calculus 1 again, right? Now, here I can write y prime equals e to the u, it means e to the tan x, times du over dx. Your du over dx is what? Secant squared times secant squared x. Really easy, not difficult, right? Just remember, when you have e to the u, it's always equals e to the u times du dx. Correct? Let's do another one. Again, example, differentiate. Y equals e to the power of negative 4x sine of 5x. This example is a little bit more complicated than the first example, because here you see, if you remember from calculus 1, you are dealing with the product rule, correct? E to the power of, I don't know who was your professor. This part is f, it's one function. Sine of 5x is another function. You have f times g. And you know that d over dx, the derivative of f times g, equals f times g prime plus f prime g, right? That's the rule, product rule of derivatives. Let's apply this rule here. Plus chain rule, because here you have e to the power of negative 4x. It means you have e to the u, correct? Then I can write y prime equals f. My f is e to the power of negative 4x times g prime. What is the derivative of sine 5x? Again, you are applying here chain rule. It's not only sine x, it's sine of 5x. It means the derivative of outside, which is sine of 5x, times the derivative of inside, which is 5, plus f prime g. What is f prime? F prime is e to the u, it means e to the negative 4x times du over dx. When your u is negative 4x, then du over dx is negative 4, right? It means e to the negative 4x times negative 4 times g, which is sine of 5x. Let's simplify a little bit here and we are done. You see, I have here e to the negative 4x. I have here e to the negative 4x. Between these two terms, I can take e to the negative 4x as a common. Then I can write y prime equals e to the negative 4x times what left here? 5 sine 5x. Negative times positive gives you negative 4 sine 5x. Here, a small mistake. The derivative of sine 5x gives you cosine 5x. I'm sorry for this mistake. I didn't focus. The derivative of g, the derivative of outside, the derivative of sine 5x gives you cosine 5x times 5x. Here, a small correction. I'm sorry. Here you have 5 cosine of 5x minus 4 sine 5x. That will be your answer for this problem. Only mistake that I didn't focus, the derivative of sine is cosine, right? This was all about the derivative of e to the power of x, correct? I give you two simple rules. If it's e to the x, the derivative of e to the x is e to the x. If it's e to the u, then it's e to the u times du dx, correct? Let's talk about the limit. Limit of e to the x. Let me write at least once the limit in a nice way. Limit of e to the x. What is the limit of e to the x? Number one, the limit of e to the x as x approaching to negative infinity is always 0. Why? Look at the graph. X, y. This is the graph of e to the x. Correct? This is 1 and 0. As x approaching to the negative infinity, to this side, where the graph goes to 0. That's why you have the limit of e to the x as x approaching to negative infinity, always 0. Number two, limit of e to the x as x approaching to positive infinity you can see when your x is approaching to positive infinity, the graph goes also to infinity. Right? Two rules for the limit of e to the x. Correct? You have to remember these two. Let's do an example to practice this limit. Find limit of e to the power of 2x over e to the power of 2x plus 1 as x approaching to infinity. Remember from calculus 1, when you have a limit problem, the first thing to do is you have to plug in the number, correct? That's the easy way. First check, plug in the number. If I plug in here infinity, e to the 2 times infinity definitely gives you infinity, correct? And here it gives you infinity plus 1, which is infinity. It gives you infinity over infinity. And if you remember from your calculus 1 class, when you are dealing with infinity over infinity, you have a rule that you are dividing the numerator and denominator by the highest exponent of denominator, correct? Later in this chapter, I give you a rule for these types of the limits, which is much easier than this classic way that you learn in calculus 1, but for time being, I'm using that method, correct? But I think in 6.5 or 6.6, I give you the L'Hopital's rule, a different way of dealing with this forms of the limit, right? But right now, let's divide the top and bottom by the highest exponent of e, which is e to the 2x, correct? Then you can write limit of, as x approaching to infinity, e to the power of 2x divided by e to the power of 2x over e to the power of 2x divided by e to the power of 2x plus 1 over e to the power of 2x. Let's simplify. Limit as x approaching to infinity, e to the power of 2x divided by e to the power of 2x gives you 1. Correct? Some students, I remember in many classes, e to the power of 2x over e to the power of 2x. What is the answer? Nothing. They give me nothing. Nothing is not an algebra, correct? E to the power of 2x over e to the power of 2x gives you always 1. Here, e to the power of 2x divided by e to the power of 2x is 1. Plus 1 over e to the power of 2x. Now let's apply, let's plug in infinity there. If you plug in infinity, it gives you 1 over 1 plus limit of 1 over e to the power of 2x as x approaching to infinity. If you plug in here infinity, it gives you 1 over infinity, right? When you are dealing with the limit, a constant over infinity, your answer from calculus 1, we explained to you when you have a constant over infinity, your answer is always 0. It means this part becomes 0. It means you end up with 1 over 1 plus 0, which gives you what? 1. Our next topic is integration. Very easy, integration. Integration of what? E to the x, right? Okay, I just explained for you that d over dx of e to the x gives you always e to the x. And we know integration or antiderivative, they are opposite processes, right? integration and derivatives, they are opposite processes, not opposite functions, opposite processes, correct? If d over dx of e to the x gives you e to the x, then you can say easily integral of e to the x dx is always e to the x. That's your rule. The integral of e to the x dx gives you also e to the x. All right, let's do like 1 or 2 examples for this formula. Example number 1. Integral of x squared e to the power of x cubed dx. I don't have problem to explain for you what is the integral of e to the x cubed. Hopefully, in calculus 1, you learned the substitution method if I have integral of f of g of x times g prime of x, correct? In this case, I can write this one as an integral of u du, right? When you have a composite function and the derivative of this composite function is outside, you can see it, then you can write it as an integral of u du, right? Here you see e to the power of x cubed is actually a composite function. Your g of x is x cubed. You see, your g of x is actually x cubed. What is g prime of x? G prime of x gives you 3x squared. You see x squared, you have here x squared. Then use the substitution rule. I don't have time to explain again the substitution rule for you here in calculus 2. Hopefully you learned it very well in calculus 1, right? Then I can write this one. I'll put u as an x cubed. Let me erase here all these extra explanations for you and apply the substitution rule for you, right? Your u is x to the power of 3. Then your du equals 3x squared dx. If you solve this one for x squared dx, 1/3 of du equals x squared dx. To solve for x squared dx, you divide both sides by 3, correct? That gives you du over 3, or 1/3 of du equals x squared dx. Now you see, you have all pieces of substitution here. You replace x squared dx with 1/3 of du, and you replace your x cubed with u. Then you can write this one as an integral of e to the u. You see here I have x squared and dx. I replace x squared and dx with what? 1/3 of du. 1/3 du. When you have a constant, you can move your constant outside of integral, right? Then you can write 1/3 integral of e to the u du. And now everyone knows what is integral of e to the u. Integral of e to the u gives you back e to the u, because you are dealing with indefinite integral, you have to put here plus c. Correct? One more step. 1/3 of e to the power of, what was your u? Your u was x cubed. 1/3 of e to the x cubed plus c, final answer. Correct? please review the substitution rules, some important rules of derivatives that you learn in Calculus 1. For example, the derivatives of trigonometric functions, the substitution rule. These are the rules that you have to have it in the top of your mind to use it here. I'll try to explain a little bit for you, but there is no time for us to cover those topics again. It's only a 6-week course, right? And we have to finish six chapters. Example number 2. Find the area under the curve y equals e to the power of negative 3x from 0 to 1. Again, we are going back to calculus 1. Find the area. What is area in the calculus when you are looking for the area under the curve? For example, if I draw this problem for you, you have e to the power of negative 3x. Somehow, let's say this is the graph, right? You are looking for the area from 0 to 1, this area, right? Finding this area. How to find this area? Area for us in calculus means look for the integral of this given function, correct? The area is equal integral of e to the power of negative 3x from where to where? From 0 to 1. These are the upper and lower limits, or maybe your professor told you on that time, the upper bound and lower bound. Upper limit, lower limit, correct? You are looking for the area under this curve. One of the main branches of calculus, calculus has 2 branches. Your professor explained in calculus 1 for you the history of the calculus a little bit. Hopefully they did for you. One of the main discussion in the calculus, or the first branch of calculus, is derivatives. Derivatives for me is the slope of the tangent line. Slope of the tangent line means rate of change. The first focus on the calculus, which Sir Isaac Newton focused on, is to find the rate of change, correct? The second branch of calculus, which more Leibniz focused on that part, is integration. He was really interested to find the areas under the curve, right? For example, here, area under the curve. And that's why we are dealing with the integral, with second branch of calculus, correct? And whenever you talk, especially when you are talking about definite integrals with these bounds, it means you're looking for a limit, for an area, correct? To find an area. Okay, anyway, that was extra explanation. Find the area under the curve y equal e to the negative 3x. My area equals integral from 0 to 1 e to the power of negative 3x. Okay, now let's apply our rule, correct? You have negative 3x here. Your u as, again, you see you are using the substitution rule because I know here I have actually 1 dx, and the derivative of negative 3x is a constant, and I have it there. That's why I'm using, again, the substitution rule. Your u is negative 3x. Then du equals negative 3 dx. And if you solve for dx, negative 1/3 of du equals dx. Wow. You have all pieces of substitution. You replace your 3x with u, you replace 1 dx with negative 1/3 of du. Then you can write a equals integral from 0 to 1 e to the u, and instead of dx, you can write negative 1/3 of du. Again, you can move the constant outside. A equals negative 1/3 integral from 0 to 1 e to the u du. You can change the bounds, the upper limit and lower limit, but do at the end use u, or if you are not changing like me the bounds, in this problem I'm not changing the upper limit and lower limit. In this case, I will rewrite the value of u here, correct? But before that, a equals negative 1/3. What is integral of e to the u from 0 to 1? It gives you e to the u, even I don't need a parenthesis here. One-third of integral of e to the u gives you back e to the u, but because you are dealing with definite integrals from where to where? From 0 to 1. What is u? Let's plug in the value of u. A equals negative 1/3 e to the power of negative 3x from 0 to 1. To plug in the values, negative 1/3 times, plug in the upper limit, it gives you e to the power of negative 3 times 1, minus plug in the lower limit, which gives you e to the power of negative 3 times 0. But you end up with negative 1/3 e to the power of negative 3 minus this one gives you e to the power of 0. Negative 1/3 times e to the power of negative 3 minus what is e to the power of 0? E to the power of 0 is always 1, right? From algebra. Distribute the negative 1/3 or just distribute the negative to inside. It gives you 1/3 of, if you distribute the negative here, it gives you negative e to the negative 3 plus 1, right? Or you can write in a nice way, it's equal 1/3 of 1 minus e to the power of negative 3. That is the area under the curve of e to the power of negative 3x from 0 to 1, correct? That will be the area under that curve. This was all about 6.2 of your lecture. Your next lecture will be 6.3. Please review this lecture a few times. The video is available in your Canvas, and do your homework. It's not that difficult. The boxes that I put for you to memorize, please memorize those boxes. I will stop the lecture here and see you next time.